Let's discuss delta H considering heat capacities. Why would we do that, you ask? Well, let me show you. Let's think about H, the enthalpy of a substance, which is the heat of 1 mole of that substance at a given temperature at a constant pressure. We haven't really thought about enthalpy so much. We've always thought about the change in enthalpy, but substances have a heat. So the enthalpy is the heat that 1 mole of that substance has at a given temperature, particular pressure. So if we take that substance and we heat it up, well, now we're increasing its heat, we're increasing its enthalpy. And we can determine that that change in enthalpy is simply the molar heat capacity at constant pressure, Cp, times the change in temperature. That's straightforward using the heat capacity definitions, right? The heat capacity is the amount of heat needed to raise the temperature of 1 mole of a substance by 1 Kelvin. So here we got 1 mole of its substance, got its particular H, and so we're increasing the H as defined by the heat capacity. Now, of course, change is final minus initial, so we'll just say, well, the enthalpy at T2 minus the enthalpy at T1 is Cp delta T. And let's apply that to a chemical reaction in which we're saying that delta H, the change in enthalpy, is simply the sum of the enthalpy of the products minus the sum of the enthalpies of the reactants. Okay? So in this particular case, our products are 2B, so we got twice the enthalpy of B. Reactant is an A, so minus the enthalpy of A. Now let's pretend that delta H changes with temperature. So we'll say, well, at T1, so we'll make that the lower temperature, delta H of the reaction at T1 is twice times the entropy of B at T1 minus the entropy at A at T1. I've just taken this equation here and I've specified, well, it's at a particular temperature T1. Now I'll do the same at a different temperature that we'll say is a higher temperature T2. But exactly the same idea. I'm just taking this equation here and plopping it in at 2 different temperatures. Now let's combine those 2 equations by subtracting the T1 from the T2. So all I've done here is I've said, well, delta H at T2 minus delta H at T1 is taking these blue, green, and red relationships here and popping them in here. So here's the T2 one, 2B's minus an A. Here's the T1 one, 2B's minus an A, and I'm taking the T1 from the T2. Now let me collect green terms. So no change over here to the left-hand side. I've just rearranged it, so I've got my T1 for B in here with the T2 for B. Of course, there's 2 each of them because there's 2 moles of B. And then here I've got the red ones, the T2 of A minus the T1 of A. Let's bring the 2 outside the brackets, just to make it a little bit clearer. So now inside these brackets, in this green one here, I've got the enthalpy at T2 of a substance minus the enthalpy at T1 of that same substance. Here I've got the enthalpy of a different substance at T2 minus the enthalpy of that different substance at T1. Well, this here, what's exactly inside the curly brackets, is right here, isn't it? Enthalpy of a substance at T2 minus the enthalpy of a substance at T1 is just Cp of that substance times delta T. So let's pop that in here. Left-hand side doesn't change, 2 doesn't change, but this now becomes the Cp of B times delta T, and this is the Cp of A times delta T. Makes it look a little bit more palatable, okay? Now, again, simple simplification, not going to change the left-hand side, but I've got delta T's in 2 different places on the right-hand side. Let's pull delta T out, shall we? So now delta HT1 minus T2, minus delta HT1 is twice times the Cp of B minus the Cp of A times the change in temperature. Now look at now what's inside the curly brackets. We got 2 of the Cp of B minus the Cp of A. Isn't that just the sum of the Cp's of the products minus the sum of the Cp's of the reactants? Let's pull that out here. Okay. Delta Cp, call it delta Cp, is where we sum up the CPs of the products using the coefficients as we always have, sum up the CPs of the reactants using the coefficients as we always have, and subtract them from each other. Now look at this equation here. We've now changed it to delta HT2 is equal to delta HT1 times that whole delta Cp times delta T, write it out like that, to get so-called Kirchhoff's equation. Might be Kirchhoff's, but I like it Kirchhoff's equation. That's the same Kirchhoff that you might have encountered in physics with circuits, that you will encounter in spectroscopy. He was rather a clever chap. I'm not sure if he really did all those things, but he certainly has an awful lot of nice stuff ascribed to him. But this particular Kirchhoff's equation says that delta H changes with temperature, and the new delta H is equal to the old delta H plus this delta Cp, where you figure out the relationships between the Cp's of all the products and the reactants, times the change in temperature. Now, if we were in a deeper physical chemistry class, this would be a nasty looking partial differential equation, but we're not going to worry about that. What I'm worried about here is the important concept. Hopefully it kind of makes a little bit of sense to you. Delta H at a particular reaction temperature compared to delta H at a different temperature, that relationship is going to be associated by how much heat is needed to be absorbed by all the different substances associated with that temperature change.